Assalamualaikum warahmatullahi wabarakatuh and good day. This is the lecture for BMFG1213 Engineering Materials. My name is Dr. Muhammad Shahdan bin Muhammad Swan and I will be talking about Chapter 12A, Functional Properties of Materials, Electrical Conduction and Semiconductivity. This topic will cover the CLO2, which is analyze the properties of engineering materials based on its structure. This is the outlines of this chapter 12.1 Electrical Conduction, 12.2 Semiconductivity. So, at the end of this chapter, you should be able to first define conductivity, semiconductivity, insulative properties of materials. Second, you can describe four possible electron band structures for solid materials. Then, briefly describe electron excitation events that produce free electrons or holes in metals, semiconductors, and insulators. And finally, you can define intrinsic and extrinsic semiconductors and how charge is transported in such. The first content of this lecture, 12.1 Electrical Conduction. So as the introduction, in the designing process of some products of components, consideration of the electrical properties of materials is crucial during materials and process selection processes. For example, the electrical behaviors of the various materials that are used in the different components of an integrated circuit package are diverse. Some need to be highly electrical conductive, whereas others need to be electrical insulative, depends on their applications. In this slide, we can see that there are three types of electrical properties of materials. The first one is conductors, the second one is semiconductors, the third one is insulators. While the figure below shows the metaphor of these properties. The conductors is just like a highway where the cars can speed at high or maximum velocity, while for semiconductors it's just like a federal road that the speed depends on the condition. While for insulators it's just like a broken bridge where we cannot cross the river. So next is the definition of the properties. The first one is conductors. Conductors have low resistance which allows electrical current flow. For example, copper, silver, gold, aluminum, and nickel. While for insulators have high resistance which suppress electrical current flow such as glass, ceramic, plastics, and woods. While semiconductors can only allow or suppress electrical current flow, for example, carbon, silicon, and germanium. Or we can say that the R or the resistance in conductor is low. R for insulator is high, while for semiconductors the R is depends. Okay. This is the atomic structure of conductors. The atomic structure of good conductors usually includes only one electron in their outer shell. It is called a valence electron in here. It is easily stripped from the atom and producing current flow. This is the valence electron. Free electron from outer shells of metal atoms can easily strip from the atom and producing the current flow. So the valence electron easily freed from to form the current flow. This is an example for copper atom. While for insulators have a high resistance, so current does not flow in them. For example, glass, ceramic, plastic, and woods. This is the view of an integrated circuit. Scanning electron microscope images of an IC. IC is integrated circuit. We can see that a dot map showing location of silicon, a semiconductor. Silicon shows up as light regions. The first one, this is the light region is Si. The light region is Si, semiconductor. A dot map showing location of aluminum. A conductor, aluminum shows as light regions. Okay, in this figure, the light region is aluminum. So we can see that there are two types of electrical properties in IC. The first one is semiconductor. The second one is conductor. Combination of silicon and aluminum. How does the electric can be conduct? First of all, we need to know the electron arrangement in atom structure. The first bond is metallic bond. For metallic bonds, make free movement of valence electrons possible. Outer valence electrons are completely free to move between positive ion core. Positive ion core vibrate with greater amplitude with increasing temperature. The motion of electrons are random and resistant in absence of electric field. In the absence of electric field, the electrons are freely moved and randomly move from one to another core. Can jump from the first positive core into the other positive core. But in the presence of electric field, electrons attain directed drift velocity. Or in the presence of electric field, such as this is the direction of electric field. So the electron, the free electron will move from this direction into this direction. Okay. Or we can say that by applying the electric field, the negative and positive, the electron will move to the positive side. When we talk about electrical conductivity, we must know the very important law, which is the Ohm's law. Ohm's law states that electric current flow I is directly proportional to the applied voltage V and inversely proportional to resistance of the wire. I equal to V over R, or V equal to I R, where I is the electric current, V is potential difference, R is resistance of wire. Electrical resistance R is related to electric resistivity ρ, material resistance toward conducting electrical current S. R equal to ρ L over A, where the L is the length. L in here is the length of the conductor. A is the cross-sectional area of the conductor. Let's say you have a cylinder wire in here. So the A will be pi r square. It depends on your sample. Electrical conductivity sigma reciprocal of the resistivity 1 over rho. Ohm's law can also be expressed by using this formula J equal to E over rho, or equal to sigma multiplied by E, the Ohm's law. J is the current density, while E is the electric field, V over M. We can see in this table different value of different metals. The first one is silver, copper, gold, aluminum. We can see in here the silver have the highest conductivity compared to the other and the metal. Suppose suppose gold to be the first. Maybe it's not the pure gold. So in this case, the silver is number one, copper number two, gold number three, while aluminium is number four. And for the case of non-metals such as germanium and silicon, the electric conductivity is much lower compared to metal. But for the polyethylene polymer and also the diamond ceramic, it has very low electrical conductivity or very high electrical resistance. So this is you can do by yourself. This is the Ohm's law example. A wire whose diameter is 0.25 centimeter must carry a 25 ampere current. The maximum power dissipation along the wire is 5 watt per meter. Calculate the minimum allowable conductivity of the wire in ohm meter for this application. So this is the solution you can do by yourself. First, you need to know how to calculate the power. Power is equal to P equal to IV or I square R. Then combining these two equations can give you this equation. Rearranging the formula, you can have the electrical conductivity in here. Given that the P is 5 watt and you just insert the value, finally you got the final answer is 2.55 multiplied by 10 to the power of 7 ohm meter minus 1. Energy bands in solids. The magnitude of electrical conductivity strongly depends on the number of electrons available to participate in the conduction process. So not all of the electron can conduct the electric. The conductivity of a semiconductor increase with the increasing temperature, behavior opposite to that of a metal. The number of electrons available for electrical conduction in a particular material is related to the arrangement of electron states with respect to the energy, and then the manner in which these states are occupied by electrons. The figure shows the shells and shells are showed by integers 1, 2, 3 and subshells by letter S, P, D, F. For each S, P, D, and F subshells, there exists respectively 1, 3, 5, and 7 states. Each state can be occupied by 2 electrons having opposite spin. A solid may be considered of as consisting of a large number of atoms n, initially separated from one another, which are subsequently brought together and bonded to form a crystalline material. As the atoms come within close proximity of one another, electrons are perturbed by the electrons and nuclei of adjacent atoms. This influence causes each distinct atomic state to split into a series of closely spaced electron states in the solid to form an electron energy band. The number of states within each band will equal the total of all states contributed by the n atoms. For example, n is 12. For example, an S band would consist of n states and a P band of 3 n states. This is the example of electron energy band. This is the first band, while this is the second band. So each band contains 12 states. The extent of splitting depends on interatomic separation and begins with the outermost electron shells, as they are the first to be disturbed. as the atoms come together. Within each band, the energy states are discrete, yet the difference between adjacent states is very small. At the equilibrium spacing, band formation may not occur for the electron subshells nearest the nucleus as shown in figure B. Furthermore, gaps may exist between adjacent bands, as also indicated in the figure. Normally, energies within these band gaps cannot be occupied by electron. The conventional way of representing electron band structures in solid is shown in figure A. Figure A shows the conventional way of representing electron band structure in solid. So rather than using this kind of figure, we will use this type of figure, which is easier to understand the energy band. The electrical properties of a solid material are a consequence of its electron band structure. In other words, they are influenced by the arrangement of the outermost electron bands and the way in which they are filled with electrons. Four different types of band structures are possible at 0 Kelvin. They are shown here as A to D. This is the A type. The energy band structure in A is represented by some metals, in particular those that have a single s valence electron, for example copper. So in this case, copper atom has 4s electron. Only half the available electron positions within this 4s band are filled. The energy corresponding to the highest filled state at 0 Kelvin is called the Fermi energy level or Fermi energy EF. This one field state which is 4s electron. This is the Fermi energy EF, while this is the band gap and empty state. The second type of band structure B, this is the second type, is also found in metals. There is an overlap of an empty band and a filled band. So there is overlap in here between the empty band and filled band, such as the magnesium shows this band structure. Each isolated magnesium atom has two 3s electrons. However, when the solid is formed, the 3s and 3p bands overlap. So 3s and 3p band will overlap. That's why the magnesium, some kind of metal, can conduct electric easily, because the field band is overlapped with the empty band. So the electron from field band can moving from field band to empty band. The final two band structures are similar. One band, the valence band that is completely filled with electron, is separated from an empty conduction band, and an energy band gap lies between them. So this is quite similar. There are valence band, band gap, and empty conduction band. So similar, band gap and also empty conduction band. But the difference between these two are lies in the magnitude of the energy gap. So we can see in here the energy gap for insulator is bigger than compared to the band gap of semiconductor. For materials that are insulators, the band gap is relatively wider, whereas for semiconductors it is narrow, as shown in figure D. The Fermi energy for these two band structures is located near the center of the band gap. Okay, this is the center of the band gap. This is the EF. So we can see in here EF for semiconductor is lower than the insulator. Conduction in terms of energy band model. Only electrons with energies greater than the Fermi energy may be acted on and accelerated in the presence of electric field. So the electrons in the greater than Fermi energy can be used to conduct electricity. These are the electrons that participate in the conduction process and termed as free electrons. Another charged electronic entity called holes is found in semiconductors and insulators. Holes have energies less than EF or Fermi energy and also participate in electronic conduction. A hole is the absence of an electron in a particular place in an atom, although it is not physical particle in the same sense as an electron. A hole can be passed from atom to atom in semiconductor material. A hole forms in an atom when the electron moves from the so-called valence band, the shell outside the closed shell that is partially or completely filled with electrons, into the conduction band. So this is the conduction in metals. Energy band structure for metal, insulator and semiconductor. We can see for metal, there are overlap of call the conduction band and also the valence band. While for insulator, the gap is much bigger compared to semiconductor. For metals, there are vacant energy states adjacent to the highest field state that EF. Thus, very little energy is required to promote electron into the low lying empty state as shown in figure A. And in here, generally, the energy provided by an electric field is enough to excite large numbers of electrons into these conducting states. This one is for metal. For insulators and semiconductors, empty states adjacent to the top of the field valence band are not available. To become free, the electrons must be promoted across the energy band and into states at the bottom of the conduction. This is possible only by supplying to an electron the difference in energy between these two states, which is approximately equal to the band energy gap or band gap energy. This excitation process is shown above. For many materials, this band gap is several electron volts wide. Normally, the excitation energy is from non-electrical source such as heat or light, or usually the former. We can see in this figure, for the metal, the band between the conduction band and valence band is overlap in here. While for semiconductor, the band gap, there's still band gap, but the band gap is uh, narrow compared to the band gap of insulator. So it just need excitation energy for semiconductor. For the electron from the valence band goes into the conduction band. The excitation energy such as the heat or light can be used to excite the electron from the valence band into the conduction band. Okay, so this is the end of the part 1. We will continue about the semiconductivity properties of materials in part 2. Thank you.